All right, I should have brought the screen down first. Let's go through a few slides that illustrate some of the concepts we've been talking about, and then we'll start talking about how all this works out.
Any fire please?
Too bad for you.
I like this. Learning types of things instead of math.
Oh, the math is coming. Don't worry.
Let's go.
Yeah, we're not just doing classification here. There's classification's important, but it's not all classification. Yeah. Well, then, you know, it is a difference between I mean, particle physics can be this way to some extent, but, you know, in astronomy astronomy studies natural history and things like that, and so a big difference between physics and astronomy is that we have this natural history focus in many ways, you know, what is the history of galaxies and so on and so forth, as opposed to just trying to uncover fundamental laws of nature or applying it to figure out the story, right, of the universe and its various components. So we need physics to do that. So we have that natural history emphasis that physics typically does not.
I know how this works, but I have no idea what it is.
Me in every sense.
That's right. But,
Put that up. Oh, hello.
All right, I don't want to sit right next to you. I want to see if I can force that over a little bit. Because it's not quite lined up, right? So there we go. That's better. That's better? Okay. So now the image is going off the edge of the screen like it was.
This is under mass access.
That's right, yes. Uh-huh. Okay. So, hey Diego. There we go.
The salad is not as good as the last one I had.
So remember, we have the binary star system. They both move on ellipses. Both ellipses have the same eccentricity, but the more massive object moves on a smaller ellipse, and the ratio of the semi-major axes is the reciprocal of the ratio of the masses. And as they orbit, the center of mass is always on the line joining them, because center of masses do that. And so they dance around the center of mass generically like that. You can always connect the two of them, and that has to go through the center of mass of the system. And then I think I showed you guys this before, right? This thing where it shows, yeah. What's that?
I think so.
Yeah, I did, where we showed like, whee!
Oh, yeah.
All that, yeah. So I won't do that again. Here's a visual binary where its relative orbit was plotted over quite a long period. So you can see what the earliest is like 1825, and the latest is like 1912. So these are old data, but what's that?
It's the longest lab ever.
It's the longest lab ever. That's right. Yes. I'm guessing that the later work wasn't done by the people who started it. And if it was done by the people who started it, I'm very impressed by the people that started it. They must have been exercising and eating right. But in any case, the period is 87.7 years. So if they started when they were 20, they were 107.7 or something like that. Anyway, relative orbit. So in other words, when we say the relative orbit, you keep plotting one star in the same position, and then you plot where the other star is relative to it, which, if you think about it, is exactly what we're talking about when we find the orbit of the reduced mass in the equivalent one-body problem. So what this is a plot of is the orbit of the reduced mass for this system. And if you knew how far away the system was, you could translate the angular size of the orbit into an actual physical size of the orbit. Here is a figure from the text which shows the idea of an astrometric binary. So the visual member wobbles across the sky, and the unseen companion must also do the same thing, but we don't see it. Center of mass is always on the line joining between them. So why isn't the path of the visual member simply an ellipse? What's going on there? int. So suppose that,
So we're seeing it side on.
it's not so much that, suppose that, suppose that my elbow is the center of some circular orbit, okay? And relative to the room, is my finger tracing out a circle right now? No, it's tracing out some weird old curlicue thing, right? So I ask again, what's happening here? Why isn't that shape that we see in ellipse?
It's because we're moving?
Or the star is moving, or whatever, right? Motion is relative. So in other words, there is relative motion between the binary system and us. And so not only do you see the elliptical motion of the visual member, but it's superimposed on that is the motion of that system through space relative to us. So in general, binary star systems are moving relative to us. So you have to correct for that, potentially, in order to see the shape of the orbits. So I will leave this up and talk about what that is illustrating. That's what's coming next here.
Put it on an incline.
What's that?
I said you put it on an incline.
Put it on an incline, that's right. Tip it.
Trees would be proud.
Yes. All right, so we'll start talking about the first example there, visual binaries for which we can plot both orbits and determine the period, and for which we know the distance. So let's illuminate you guys better. And come over here.
We're like look at each other and like there's no actual like sentence going on. We're just like, we're like shrugging.
What?
So I've noticed whenever like Derek and I like we just kind of like look at each other during anything, we'll either like just start nodding for no reason, or we'll shrug and we're just like, and it's like a nonverbal communication. I don't know what we're communicating, but that's just that's just what happens. I don't know why.
Okay, that's interesting. So when you're communicating with Nicole, is it sometimes like
That's actually every single time.
that look of like, you will never change, will you?
Whenever I'm doing something, I look over at Nicole to see what her reaction is to what I'm doing, and then I know, am I supposed to be doing this, or am I supposed to be doing something else that I don't know about?
Right. It's very useful that way.
Yes. I'll sit down and play Guitar Hero and I'll be like, then if she's not looking at me, then I'm like, okay, I'm good, I can keep playing. If you give me this look, then I know, oh, no, I gotta stop, I gotta figure something else out.
Just have either blinders or just close the door. So she can.
So then I can't. So that could be worse, because then I can change her look from a look of you should be doing that to a look of why the hell are you doing that?
Mass determination using visual binaries. So, just as I showed you at the beginning there, often we see a plot of the relative orbit of the two stars. Or in other words, the orbit of one star relative to the other. Which is always plotted as the origin. Which referring to the other star. So one star is plotted at the origin, you plot where the other star is relative to it. This is, in fact, the relative displacement of the reduced mass. So you're really plotting mu when you do that. Or actually, you're plotting the projection of mu onto you're plotting not mu, you're plotting the order of mu, or actually you're plotting its projection onto the plane of the sky, because the tricky part is the fact that if the orbit is a circle, the orbit won't necessarily look like a circle, because if the orbit is tipped, it makes the circle look flattened. So I'll draw a generic picture on the sky here. North, east, west, south. So we do it in terms of celestial coordinates, right ascension and declination. You can do it in that grid. So you've got north, south, east, west. Why are east and west backwards on there? Relative to a map of the Earth, right? On a map of the Earth, if north is up, east is on the right. On a map of the sky, east is on the left. Why is that? Because we see the sky from the inside, so to speak, right? And we define east on the celestial sphere to be the direction towards the eastern horizon. If we're looking at something above the horizon, if I'm facing south right now, then north is towards the north celestial pole, south is towards the south celestial pole, and if I'm facing south, the eastern horizon is on my left. So on sky maps, east and west are reversed compared to what they are on Earth maps. Another way to think of that is we're looking at the sky from the inside. If you were inside the Earth, good luck, looking at the United States, you'd see a backwards United States. East would be on the left, and west would be on the right. And so that's what we're seeing on the sky, so to speak. And so the way one of these plots works, I'll draw something generic here, is, and that's supposed to be symmetric, let me help. Actually, let's think about it. Does it have to be symmetric? Maybe not. I'd have to think about it. Anyway, I don't care. It doesn't matter for these purposes. So, this angle right here, away from north, is called the position angle. So the angle away from north is the position angle. And if we call the two stars A and B, then we always plot A at the origin, and then we plot where B is relative to A on the sky. Just like, I should put my first picture up again. Not. And of course, in reality, there's going to be errors, and so you would fit the curve. Yeah, it doesn't have to be symmetric, so never mind. I deliberately drew it asymmetric, just like I said. So, what am I trying to say there? So there's going to be error bars, right? There's going to be errors, and so you have to fit a curve, certainly. Displacements will be measured in arc seconds because that's what we can measure on the sky. We measure angles on the sky. And typically, we're talking about arc seconds when we are able to make measurements like this. If we can do the measurements, we find that arc seconds is the kind of angles that we're looking at through the telescope. If the orbit is in the plane of the sky, what does it mean to say plane of the sky, do you think? What does it mean relative to, in terms of the line of sight, if the orbit is in the quote-unquote plane of the sky? Because of course the sky doesn't literally have a plane, but if you think of the celestial sphere, if you pretend that there's a celestial sphere surrounding us, the plane of the sky at any given point is, imagine a plane that is tangent to the celestial sphere at that point. So how is that oriented relative to our line of sight? How is that plane oriented relative to our line of sight? If it's perpendicular line of sight. Right? So if this is our line of sight, the plane of the sky is the plane perpendicular to our line of sight. So we just call that the plane of the sky. If the orbit is in the plane of the sky, then we see its true shape. Plane of sky means perpendicular to line of sight. In that case, A is alpha times D, where A is the semi-major axis of the orbit in AU, alpha is the angular semi-major axis in arc seconds, and D is the distance in what unit, would you think? So we're setting up a big triangle, if you will. That actually worked out pretty well. So that's alpha, the angular apparent size of the semi-major axis of the orbit that we see. A is its actual size. So what should our distance be here? What distance unit connects AU and arc seconds to one another? Not light years, the other one. Parsecs. Parsecs. D is the distance in parsecs. Because remember, by definition, 1 AU subtends 1 arc second from a distance of 1 parsec. So we have a simple relationship that the semi-major axis in AU is the distance in parsecs times the apparent semi-major axis in seconds of arc. How convenient. Now, remember that A is equal to A1 plus A2. In other words, the semi-major axis of the relative orbit is the sum of the semi-major axis of the two actual orbits relative to the center of mass. The sizes of the orbits are additive. A1 and A2 are the semi-major axes of the individual stellar orbits. Now, if we can see these guys well enough that we can actually plot the individual orbits, we can see how they're moving relative to what, we should be able to see how they're actually moving relative to the sky. If we can determine the actual two individual orbits, we know A1 and A2, and so that ratio gives us the ratio of the two masses. And the orbital period and A give us the sum of the masses. That's the key here. Remember, Kepler's third law relates the sum of the masses to the square of the period, the square of the period and the cube of the semi-major axis. And the ratio of the semi-major axes tells us the ratio of the masses. So, if we plot the individual stone orbits, note that we have to subtract off the motion of the system through space. To subtract off the motion of the system relative to us. We can find m1 over m2, since that's just a2 over a1. But that'll be alpha 2 over alpha 1. In other words, we don't actually have to know the number of AU for A2 and A1 for this. We just need to know the number of arc seconds because both of them have that same factor of D in them. So in other words, we don't need to know D to find the mass ratio, as I mentioned before. There you just need to know how big are the two orbits relative to one another. But if you want to find the actual masses, then you do need to know the distance, because only then can you find out what A is. From Kepler's third law, we know m1 plus m2 is equal to 4 pi squared over g times a cubed over p squared that's in SI units, right? So there I would really in any units, but we can choose units where 4 pi squared over g is equal to 1, much more conveniently. But if I knew A in meters and P in seconds, then I could plug in and find the sum of the masses in kilograms. That's not what I want to do, because again, it's really better to find the masses in terms of the sun's mass. If we use A in AU and P in Earth years, this just becomes m1 plus m2 is equal to a cubed over p squared, where A is in AU, P is in years, and m1 plus m2 is in solar masses. So you can directly get your calculations in terms of solar masses by using AU in years as your units for the distance and period of the orbit, the semi-major axis and period of the orbit. So this is the one you want to use most often. We do need to know D here. Since A is alpha D, alpha is the thing we can directly measure, so we need the distance to turn that into the actual physical size of the orbit. And then again, if I know the ratio and the sum of two numbers, I can find the individual numbers. That's two equations and two unknowns. So that's why we can determine both masses in that situation. If we know the distance and we can measure the orbits, we can find both the sum of the masses and the ratio of the masses, and then we're good to go. Tricky part. Problem. If orbit is inclined, we don't see its true shape. For example, an inclined circle looks oval, right? So in other words, if I drew a circle on this piece of paper and then I tipped it relative to you, you would see it as an oval, as an ellipse basically, instead of as a circle. That wouldn't hurt for a circle because still the major axis of the oval would be the same as the diameter of the circle, so you'd still be able to figure out what the radius is. But on the other hand, what if I had an elliptical orbit and I tilted it like this? Then the apparent semi-major axis is smaller than the actual semi-major axis. So you would get the wrong number by assuming that you were seeing the actual semi-major axis of the orbit. Okay? Turns out, and I've never done these calculations myself, so I'm just going to say, it turns out you can, and I've never been interested enough to actually see how you do it. I'll let other people do it. So I'm just perfectly happy to say there's a way to do this. And if you really want to know, go ahead and do your own research. We're just going to keep it like, turns out you can do this. Inclination angle we meaning someone else. But we could do it if we chose to learn how. And we can find the inclination angle, which we call I, which is in our figure from before, the angle of inclination of the plane of the orbit from the plane of the sky, how much it's tipped relative to the plane of the sky. We can find that angle I by utilizing the fact that the projected focus doesn't coincide with the focus of the observed ellipse. does not coincide with the focus of the observed ellipse. And I'll use this figure to explain what I mean here. So the tilt, so this is the drawn solid here, this front surface here is the actual orbit. And then back behind it with dashed lines is the projection of that orbit onto the plane of the sky, what we would actually see. So the thing to note is we can determine where the true focus is. How do we do that? How would you imagine determining where the true focus of the orbit is? You can't do it just from looking at the shape of the apparent orbit because it's distorted, so you can't do that. But what could we do to figure out where the true focus is? Go back here. What's true about the orbits? The center of mass is a focus, right? And how can I locate the center of mass? If I had multiple plots of where those two stars are, what would I do to find the center of mass?
You can draw a line between them and all the intersections.
They'll all intersect, right. I'll draw a line between them, they'll all intersect at the center of mass. Now there'll be errors, and so they won't quite intersect, but they'll, within errors, they'll all intersect at a single point. Really, they'll crisscross near a single point, and you could find some sort of average crisscross location that would represent the true center of mass. That's where the actual center of mass is. If the true shape, if the apparent orbit's apparent focus, if the focus of the apparent orbit is different from the actual focus, which you find by where all those intersections are, you know the orbit is inclined. And it turns out that if you know how far the projected focus is from the true focus, how far the projected focus is, from the true focus, the one you should determine no, that's not what I'm trying to say. The projected focus is the projected true focus. What I want to say is, how far is the apparent focus from the projected true focus? And in what direction it's displaced? It turns out you can figure out what the inclination is. You can do some geometry and figure that out. Like I say, I'm sure I could do it if I really wanted to, but I've never wanted to enough to take the time to figure it out or to look up how people do it. But it would just be a matter of looking it up or taking the time to draw some fancy pictures and figure it out. I've just never felt like doing it, but you can imagine that it is possible to do so, and it is. That's why the look on your face.
So you'll be doing this in the homework.
So you will not be doing this in the homework. That's right. Yes. So you will not be doing this in the homework, but I want you to realize that you could. Right? An obvious case of the true focus not coinciding with the projected focus is, what if you had a circular orbit? Where's the center of mass located? Where's the true focus of that circular orbit? Directly in the center. Now I see it as a tipped orbit. Is the focus of that apparent orbit in the center? No, it has two foci, right? This orbit, this apparent orbit, this ellipse, has two foci over here and here. So clearly, if I plotted for this system where the stars, where the lines intersected, you'd have a bunch of lines that intersected in the middle of the figure, right? Because the stars here, they all intersect in the middle. But that's clearly not the focus of the apparent orbit, because the apparent orbit is this flat ellipse which has two foci well displaced from the center.
So is this, it has to be a binary star system to do that because you need two stars?
Yeah, right. You'd have to see both stars in order to be able to see where the lines joining them were intersecting one another. Yeah.
Okay.
Mm-hmm. Yeah. So if you can see both stars, you can pull this off. And then you can, from that, you can figure out what the inclination is. and use that to figure out what the true shape of the orbit is, and then carry out the calculation we were talking about before. And so you can find both masses in that case. So it's okay if the orbit's inclined because you can do some geometry and unincline it, so to speak. You can do the math that allows you to see what the true shape of the orbit is. Sadly, we won't be doing it. We'll just know that we could. Now let's talk about eclipsing, because we have precious minutes of education that somebody's paying for. We can't waste them. We're like, okay, whatever. No, we can't waste them. So, I mean, we could, but we're not. Eclipsing spectroscopic binaries, and I will be doing that second case. Eclipsing spectroscopic binaries, because they are the really important case. That's where we get most of our information about star bases. So, what's on in?
Is it summer break yet?
What?
Is it summer break?
Is it summer break yet? Well, that's encouraging.
Senior year, it's
It's too early for full-blown science, that's senioritis. I said it's too early for full-blown sinusitis.
sinusoidalitis.
Yeah.
What, you don't have summer breaks anymore, you just got real life.
I'll just have a job, or I'll hopefully just have a job. This economy, that's for sure.
I think after senior year, it's no longer called summer break, it's just called unemployment.
It's just called searching for a job. Hopefully there's rebel things. That would be cool. That'd be very nice to have a job in June. Leave and then just be like, I have a month, and then go back to work.
So let's talk about what happens here. Moonlighting. Ooh. Ah, right. So, let's take the simple case of circular orbits. So there's two stars both orbiting on circles around the center of mass at the center. So star 1 is moving on the smaller orbit, star 2 on the bigger orbit, so which star has more mass? Star 1, because it's moving on the smaller orbit. And here we have scenes from the orbit, snapshots of the orbit. Here's our telescope. So here's our spectrometer, really. So there's a telescope that feeds light into a spectrometer, spreads the light out into a spectrum. And so star 1 is moving towards us right here. So its spectral lines will be, is it redshifted or blue shifted? And blue shifted, shifted to shorter wavelengths by an amount that depends on how fast it's moving towards us. Similarly, star 2 is moving away from us, so its lines will be red shifted by an amount that depends on how fast it's moving away from us. And at this moment right here, we'll see the maximum Doppler shift because they're both moving either straight at us or straight away from us. And remember, Doppler shift only cares about towards or away from us motion, not side-to-side motion, if you ignore what's called the transverse Doppler shift in relativity. You're not moving relativistically here, so we need not worry about that. So, kind of reading along here, stars in a binary system orbit their center of mass. Observations show absorption lines from both stars in the spectrum. Star 1 is moving towards the viewer, so it is blue shifted, shorter wavelengths. Star 2 is moving away from the viewer, so it is red shifted, longer wavelengths. More red shift for star 2 than blue shift for star 1 because star 2 is smaller and is moving faster on the bigger orbit. It's moving faster on the bigger orbit there. And then a quarter of an orbit later, they're both moving transverse to our line of sight. So how much Doppler shift do we see? Nothing. So the spectral lines now coincide at 0 Doppler shift. Now, half a period after the first snapshot there, now it's star 2 that's moving directly towards us, star 1 moving directly away from us. So star 2 now has maximum blue shift of its spectral lines, star 1 maximum red shift. So we flipped around compared to the first view. Another quarter of an orbit later, they're transverse again, no Doppler shift. One period later, we're back to where we began. And so we have a dance of the spectral lines, if you will. Two star sets of spectral lines Doppler shift back and forth as the two stars orbit one another. And the smaller partner, the less massive partner, is swinging around more. So my fingers are the spectral lines dancing back and forth. It's pretty cool, really. It's the dance of the spectral lines. And if you use the Doppler shift formula to convert into radial velocities, motion towards or away from us, then you'll get plots that look like generically like that one on the bottom there. And so we can figure out from the velocities of the orbits what the mass ratio is, because remember that the velocity ratio is also the reciprocal of the mass ratio. So that's true at every moment, but what you in practice do is you find the amplitude, because if you use a lot of data, you can fit a curve to it and find its amplitude. So the ratio of the velocity amplitudes is the reciprocal of the ratio of the masses. And if we know that the plane of the orbit is essentially containing our line of sight, then we know that we are at some point seeing the star move straight at us or straight away from us. If the orbit is tipped, then never is the star moving straight at us or straight away from us. We only see the component of the motion straight towards us or straight away from us. And there's no way to know what the true motion is, because there's no independent way to know what the angle of inclination of the orbit is in this case. There's no information that tells you that. But if the orbit is very nearly containing our line of sight, we'll see the two stars pass in front of one another. So the reason eclipsing spectroscopic binaries are so important is because if they're eclipsing, we know the orbit is nearly edge on. And then we know that we're seeing how fast the stars really are moving when they're moving towards us or away from us. In the case of the circular orbit, if you measure the maximum Doppler shift so that you get the maximum speed towards or away from you, that's the actual speed that the star is moving in its orbit. And that times the orbital period, how long it takes the dance of the spectral lines to repeat itself, that times the orbital period is the circumference of the orbit. In other words, we know how big the orbit is. So we can determine both masses because the velocity-amplitude ratio gives us the ratio of the masses, and how fast the stars are moving times the period gives us the actual size of the orbits. And so we're once again in a position to know both the sum of the masses from Kepler's third law and the ratio of the masses from the relation for center of mass, and we're good to go. We've got both. We've got two equations and two unknowns, and we can determine both of the masses. And I think, is this the one I set up? There's somewhere I have, maybe I just don't have it attached to the shit. I'll have to do that. It'd be a fun way to start next time. There's a simulation you can play of the dance of the spectral lines, which, you know, it's kind of cute watching. The intro students always enjoy that, especially because it lets you go like da 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 da. All right, anyway, so having set things up qualitatively, of course, next time we will be quantitative. And there was much rejoicing. Like, you mean, woo!
If this weekend doesn't kill me. So many exams coming up.
I know.
Dr. Harmon.
Yes.